So we're going to look at precipitation reactions. We're going to look and be able to predict if a precipitation reaction will occur, and we'll also be able to do something in the calculations associated with what is called selective precipitation. This is when you've got a mixture of ions in there and you want to precipitate one out and leave some behind. We'll look at that process. Okay. In our table of solubility rules, that was a long time ago, where you learned things like, oh, 1A metals are soluble salts, or that contain 1A metals are soluble, things that have nitrate are soluble, these things are insoluble. We had rules that we kind of memorized. And it tells you if you dump these ions together, you would expect to form a precipitation reaction. You should form a precipitate from solution. But we're going to take it a little further in this. We're going to say, yes, this should form a precipitate, but do we have enough ions to actually go that route? Because remember, what we didn't learn then that we now know is that even if it's insoluble, a little bit dissolves. So do we have enough ions in there to actually form that precipitate? Okay, so let's see how that's done with an example. Oh, no, we're not ready for the example yet. We're going to compare Q to K. We remember back when we first talked about equilibria that you can calculate a Q and you can calculate a K. And let me write a insoluble salt reaction. Silver chloride solid going to Ag plus Cl minus. Those are the aqueous. I kind of left out the AQ, but we know there's the aqueous. We know that the KSP expression looks like this. Once it's at equilibrium, the silver ion concentration times the Cl minus concentration, if we multiply those together, we'll get a KSP. Well, you can also do the same thing, but say, where am I right now? What is the silver ion concentration? And what is the Cl minus concentration at some other point? And that would be the Q value. Now, KSP is where it wants to be. QSP is where it is. It wants to get to this magnitude. So we figure out what's the concentration of ions in there and compare it to K. If it's an unsaturated solution, it is not going to be able to form a precipitate. That means you don't have enough of these ions present, okay? If you don't have enough of those ions present to force it to go this way, then you have a Q that's too small. So anytime you have a Q less than KSP, you have an unsaturated solution and no precipitate would form. Now, if it just so happens that you hit the right numbers where they equal each other, it's a saturated solution, okay? And you still aren't going to form a precipitate. But the scenario in which these are too big, I have too much in there, so my Q is too big, then it's a supersaturated solution. And it's going to say, I want to get out of solution, and it will go this way, and that is when you are going to have a precipitate to form. So you can memorize those Q's and KSP signs, but that wouldn't be very wise. It's easy to get them messed up. Once you have a reaction and you understand the difference between those two, you can logic your way through whether or not it should form a precipitate. So now we're ready to work a problem. Here it is. I'm going to take a sodium chromate solution and a silver nitrate solution, and I want to know whether silver chromate will form. Now, back in chemistry, General Chemistry 1, we talked about precipitation reactions, and we learned how to do the partner swap and form products. And we did something that looked like this. Sodium chromate, CrO4, that was a solution, and the other one was a silver nitrate, AgNO3. It was a solution. We did a partner swap, so we formed sodium nitrate. We formed silver chromate, CrO4. Then we decided, according to the solubility rules, if anything was soluble or insoluble. We determined that this one was aqueous and that was my solid according to rules. Or I would know it's a solid according to the fact that it says it's insoluble by that KSP being given to me. Now that is what we did when we were trying to predict the products and balance and that sort of thing. What would be the precipitate? That is not the reaction we're going to write in this, because what we're interested in is the reaction that gives us that KSP, so we can do some comparisons. So we take our insoluble salt, so don't write it this way, okay? I want to put a don't. There's nothing wrong with that reaction, it's just not going to help us. Take your insoluble salt, Ag2CrO4, there it is. And let's write its reaction that gives me that KSP value. Well, its reaction is it's an equilibrium, and I'm going to have 2 of the silver ions, aqueous, and I'm going to have 1 of the chromate ion, aqueous. Okay? And we know the KSP would be written silver's concentration times chromate's concentration, but this is going to be squared. We know Q has exactly the same look, but we're not putting in equilibrium amounts, we're putting in initial amounts. Where are we before the reaction has a chance to take place? We're going to determine this and decide how it compares to this. I was given the value for KSP of 1.1 times 10 to the minus 12. What I want to do is calculate a Q. So this is going to take a little bit of work, and I'm going to go over here on the bottom left and use some of that space in order to calculate the silver concentration and the chromate concentration that I have in solution before the reaction ever takes place. Let's get an image of what's taking place here. I have got one test tube, okay, and in this test tube it is 0.33 molar of sodium chromate, Na2Cr2O7, and it is not a test, CrO7, shoot, I want to keep doing dichromate, there, CrO4. It is not a test tube, it's a beaker, okay, so we're going to give it a beaker look now. How do I know it's a beaker? Because it's 250 milliliters, there's a lot of it, okay, so I have 250 milliliters. And then I've got myself another little beaker, and in this beaker it is 0.12 molar silver chromate, and I have 250 milliliters of it. So I've got these 2 beakers, and what am I going to do? I'm going to dump them together into a new beaker. All right, so I dump them together into this new beaker. I have a total volume of 500 milliliters now. And I'm going to dump them together and say, wait a minute, don't do anything. I want to know what your concentrations are of everything. Not of everything, of the 2 things I'm interested in. I'm interested in the concentration of silver ions. What am I doing when I dump these 2 together? I am doing a dilution. This is getting diluted by that, and that is getting diluted by this. So what's my formula for a dilution? Okay, so we're going to do the dilution formula. I'm going to come down here and see if I can do this on my knees. What you all don't know is that I've got a cast on my leg, and this is not going to be easy to get back up. All right, so I have got, I want to first get the silver concentration. Here's my source of silver, okay? So the concentration of silver is going to be done by the dilution formula. M1V1 equals M2V2. I want to know the molarity after they've been diluted. M1 is 0.12 molar. V1 is 250 milliliters. Okay? The total volume after the 2 have come together is 500 milliliters. That's going to give me a concentration of 0.06. Okay, moles per liter. Now that's of silver chromate. Is the concentration of silver the same as the concentration of silver chromate? Yes, there's 1 silver in silver chromate. So that is going to be the concentration of the silver, and I can put that in over here, 0.060. Now, let's do the similar thing, but in a different color so we can keep track of it here. Let's do a similar thing for the sodium chromate. Okay, we're going to do it in blue. To get the chromate concentration, which I need, I'm going to take the silver chromate solution. Its concentration was 0.33 molar. I had 250 milliliters of it, and I diluted it to 500 milliliters. Okay? What that is going to give me is a concentration of 0.165. Now that's of sodium chromate. Is that the same as a concentration of chromate? Yes, because there's one chromate in sodium chromate. So this is the concentration of chromate that I can put in here, 165. I'm going to keep in mind that this had to be squared, and that's going to be me QSP of a certain value. The QSP is 5.9 times 10 to the minus 4. That is the Q. All right, so before we do our comparison of Q to K, let's recap what we've done here. I want to know what's the concentration of these two ions in solution right here before they have a chance to react. I dump them together and they're each diluting the other, and so there's the dilution calculations. I take those concentrations, plug them in here, and calculate a Q. Now I'm ready to compare my Q to my K. Where's the K? It's up there. K is 1.1 times 10 to the minus 12. This is much bigger than that. So what it's saying is, wait guys, there's way too much ions in here. I want to become K, not Q. So I'm going to be able to realize, since this is bigger than where it wants to be, it's going to have to shift to precipitate, and so yes, a precipitate will form. Now what they will sometimes do in a question is, so it's not just two parts and you have a 50-50 chance of it, they don't just say, will a precipitate form? They might say, what is the value of Q? And now tell me whether precipitates form so that we know you were doing the work that was necessary. All right, let's see what's next. All right, so our next topic is something called selective precipitation. And this is when you have a mixture of ionic compounds in a beaker, okay? And you're trying to get one to precipitate out and leave the other one behind. So it's a separation technique. For those of you who are in a laboratory, you use this a lot to try to separate ions from each other to do an identification of what is in your test tube or is in your sample. But selective precipitation is going to utilize our solubility properties. So let's look at just the first level of understanding here, and that is to look at the numbers and be able to make judgments of what should precipitate first. So I've got myself a beaker, and it contains three ions, Cl minus, Br minus, and I minus. And I'm going to come along and I'm going to start adding some silver ions. So I start dripping them in. And I want to know, when I drip, which one of these is going to precipitate first? The way you know this is to know what the KSP is telling you about solubility. Will the least soluble one precipitate first? Will the most soluble one precipitate first? Which one is least, which one is most, based upon those numbers. So I want you to determine which anion is going to precipitate out first, and I'm telling you which precipitate it's going to form. Well, I'm very hopeful that you picked AgI. It is the one with the smallest KSP. The smallest KSP is the least soluble. Therefore, it'll be the first one to come out of solution. So now we're ready to try some calculations. As soon as I come back from a erased board, we're going to work on determining what the concentration of silver is going to require to make it form that precipitate. So now we're going to actually determine the concentration of silver that's going to start the precipitation of silver iodide. So I want to form a precipitate of silver iodide. This is the reaction for which that KSP is given, okay? This is what it applies to. We know that for this reaction, KSP is equal to the silver ion concentration and the I minus concentration. So what I'm not doing here is doing an ICE table in any way, shape, or form. All I'm doing is saying, I know that this test tube or this beaker already contains a certain concentration of I minus. Its concentration is 0.010 molar, right? I know that. The question is, I want to start adding silver little by little, and I want to know how much silver is going to give me the KSP of 8.3 times 10 to the minus 17. So all I have to do is divide by 0.010 on both sides, and that will tell me as I drip the silver ions into solution, I need to get the silver concentration up to 8.3 times 10 to the minus 15. As soon as it gets that, and that's not very concentrated, is it? As soon as it gets to that concentration, I want to start forming a precipitate of silver iodide. When I get to that concentration and silver iodide starts precipitating out, I keep on adding silver, and I try to get a lot of that silver iodide to come out. But eventually the next one is going to start precipitating. So I don't want to add so much that I start getting the silver bromide to precipitate out. So the key to separation is to add enough to try to precipitate out most of your iodide, but not so much that you start getting the next one to come out. So that's what our next question is about. How much I minus is going to still be there? Okay? I'm wanting to add silver, try to get most of that iodide out before I start precipitating the silver bromide. I'm curious to see, well, how much of that iodide is still going to be present once this silver bromide starts precipitating out. Now I think I can work this problem underneath this as long as I give myself ample space, and I'll do it in a different color so that we can keep track of it all. Okay, so the first thing that we're going to do is we are going to figure out on this problem, let's say first what we're going to do is we're going to figure out what is the concentration of silver that makes the bromide start to precipitate. Okay, so we're going to do a very similar process as this process here, but now for the silver bromide. Our reaction to precipitate out the silver bromide, okay, we know it's this reaction, silver plus Br minus, not putting the AQs, but we know there's AQs. We know the KSP for this reaction is the silver concentration times the bromide concentration. I plug in my KSP for the silver bromide, and its value is 7.7 times 10 to the minus 13, right? And that is going to be equal to the silver concentration that I'm trying to determine. What was in there for bromide was 0.1. So I can figure out, that's the first thing I'm doing, is what is the concentration of silver required to precipitate out the silver bromide. So when I take this divided by my 0.01, I get 7.7 times 10 to the minus 11. This is what's required to start precipitating out the silver bromide. Remember, it took less. This is what it took to precipitate the silver iodide. Starts precipitating. Between here and here, it is precipitating every bit of the way just silver iodide. Once it hits this concentration, which is a higher concentration, it's going to start precipitating out the silver bromide. So at this point, the question is, how much of that silver iodide is still present in that solution? So the second thing we're going to do is we're going to take this silver concentration and we're going to see what iodide is present. So we're going back to our KSP for this reaction. Okay, and we're going to plug this concentration in because now I know that in this test tube I have gotten my silver concentration up to this number, and I want to know, well, then what is the I minus concentration? Putting in my KSP value, which was 8.3, let's go ahead and put the 8.3 times 10 to the minus 15 here. And now solve for I minus. I minus will be 8.3 times 10 to the minus 15 divided by 7.7 times 10 to the minus 11. And that's going to be 1.1 times 10 to the minus 6. So this is how much iodine is still present when the silver bromide starts to precipitate. There's not much there. It started out as 0.01. I slowly added silver until the silver concentration got up to this, and then I started precipitating out silver iodide. I keep dripping silver ions in, and I keep precipitating silver iodide till the concentration gets up to this. At this point, it starts precipitating the silver bromide. And we've gotten that iodide all the way down to this. So we have precipitated out the vast majority of the iodide before this ever starts to precipitate. So that's what selective precipitation is all about. Now, it took me a while to work my way through this second problem here, and thinking about what's happening in the test tube will help you figure out which ones you do first. But notice, for both of these, I'm not doing an equilibrium. I'm wanting to push this reaction this way, and I'm figuring out what concentration is going to do that. So I'm really figuring out anything above this concentration will start that precipitation value, because your Q is bigger than K, and it will precipitate. All right, our next topic is leaving the world of insoluble salts and starting to look at something called Lewis acids and Lewis bases.